Data science is a process, not an event. It is the process of using data to understand different things, to understand the world.
For me, is when you have a model or a hypothesis of a problem and you try to validate that hypothesis or model with your data.
Data science is the art of uncovering the insights and trends that are hiding behind data.
It's when you translate data into a story. So you use storytelling to generate insights. And with these insights, you can make strategic choices for a company or an institution.
Data science is a field about processes and systems to extract data from various forms, whether it is an unstructured or structured form.
Data science is the study of data, like biological sciences are the study of biology, physical sciences, it's the study of physical reactions. Data is real, data has real properties, and we need to study them if we're going to work on them.
Data science involves data and some science. The definition or the name came up in the 80s and 90s when some professors were looking into the statistics curriculum, and they thought it would be better to call it data science. But what is data science? I see data science as one's attempt to work with data to find answers to questions that they are exploring. In a nutshell, it's more about data than it is about science. If you have data and you have curiosity and you're working with data and you're manipulating it, you're exploring it, the very exercise of going through, analyzing data, trying to get some answers from it is data science. Data science is relevant today because we have tons of data available. We used to worry about lack of data, now we have a data deluge. In the past we didn't have algorithms, now we have algorithms. In the past the software was expensive, now it's open source and free. In the past we couldn't store large amounts of data, now for a fraction of a cost we can have gazillions of data sets for very low cost. So the tools to work with data, the very availability of data, and the ability to store and analyze data, it's all cheap, it's all available, it's all ubiquitous, it's here. There's never been a better time to be a data scientist.
Everyone you ask will give you a slightly different description of what data science is. But most people agree that it has a significant data analysis component. Data analysis isn't new. What is new is the vast quantity of data available from massively varied sources. From log files, email, social media, sales data, patient information files, sports performance data, sensor data, security cameras, and many more besides. At the same time that there is more data available than ever, we have the computing power needed to make a useful analysis and reveal new knowledge. Data science can help organizations understand their environments, analyze existing issues, and reveal previously hidden opportunities. Data scientists can use data analysis to add to the knowledge of the organization by investigating data, exploring the best way to use it to provide value to the business. So, what is the process of data science? Many organizations will use data science to focus on a specific problem, and so it's essential to clarify the question that the organization wants answered. This first and most crucial step defines how the data science project progresses. Good data scientists are curious people who ask questions to clarify the business need. The next questions are, what data do we need to solve the problem? And where will that data come from? Data scientists can analyze structured and unstructured data from many sources, and depending on the nature of the problem, they can choose to analyze the data in different ways. Using multiple models to explore the data reveals patterns, archetypes, and outliers. Sometimes this will confirm what the organization suspects, but sometimes it will be completely new knowledge, leading the organization to a new approach. When the data has revealed its insights, the role of the data scientist becomes that of a storyteller, communicating the results to the project stakeholders. Data scientists can use powerful data visualization tools to help the stakeholders understand the nature of the results and the recommended action to take. Data science is changing the way we work. It's changing the way we use data and is changing our approach to the world.
Data science didn't really exist when I was growing up. It's not something that I ever woke up and said, I want to be a data scientist when I grow up. No, it didn't exist. I didn't know I would be working in data science.
When I grew up, there isn't that field called data science, and I think it's really new.
Data science didn't exist until 2009, 2011. Someone like DJ Patil or Andrew Gilman coined the term. Before that, there was statistics, and I didn't want to be any of those. I wanted to be in business, and then I found data science a heck of a lot more interesting.
I studied statistics. That's how I started. I went through many different stages in my life where I wanted to be a singer and then a doctor. And then I realized that I was good at math. So I chose an area that was focused in quantitative analysis. And from then I do think that I wanted to work with data, not necessarily data science as is known today.
The first time that I had contact with data science when I was my first year as a mechanical engineering, and strategic consulting firms, they use data science to make decisions. So it was my first contact with data science.
I had a complicated problem that I needed to solve, and the usual techniques that we had at the time couldn't help with that problem.
I graduated with a math degree in the worst possible time, right after the economic crisis, and you actually had to be useful to get a job. So I went and got a degree in statistics, and then I worked enough jobs that were called data scientists that I suddenly became one.
My undergraduate degree was in business, and I majored in politics, philosophy, and economics. And then I did a master's in business analytics at New York University at the Stern School of Business. When I left my undergrad, the first company I joined, it turned out that they were analyzing electronic point of sale data for retail manufacturers. And what we were doing was data science, but we only really started using that term much later. In fact, I'd say 4 or 5 years ago is when we started calling it analytics and data science.
I had several options for my internship here in Canada, and one of the options was to work with data science. I used to work with product development, but I think that was a good choice. And then I started my internship with data science.
I'm a civil engineer by training, so all engineers work with data. I would say the conventional use of data science in my life started with transportation research. I started building large models, trying to forecast traffic on streets, trying to determine congestion and greenhouse gas emissions or tailpipe emissions. So I think that's where my start was, and I started building these models when I was a graduate student at the University of Toronto, started working with very large data sets, looking at household samples of say 150,000 households, 500,000 trips, and that too I'm speaking from mid-90s when this was supposed to be a very large data set, but not in today's terms. But that's how I started. I continued working with it, and then I moved to McGill University where I was a professor of transportation engineering, and I built even bigger data models that involve data and analytics. And so I would say, yes, transportation research brought me to data science.
I've built a recommendation engine before as part of a large organization and worked through all types of engineers and accounted for different parts of the problem. It's one of the ones I'm most happy with because ultimately I came up with a very simple solution that was easy to understand from all levels, from the executives to the engineers and developers. Ultimately, it was just as efficient as something really complex that I could have spent a lot more time on.
Back in the university, we have a problem that we wanted to predict algae blooms. These algae blooms could cause a rise in toxicity of the water, and it could cause problems to the water treatment company. We couldn't predict with our chemical engineering background So we use artificial neural networks to predict when these blooms will occur. So the water treatment companies could better handle this problem.
In Toronto, the public transit is operated by Toronto Transit Commission. We call them TTC. It's one of the largest transit authorities in the region in North America. And one day they contacted me and said, we have a problem. And I said, okay, what's the problem? I said, well, we have complaints data and we would like to analyze it and we need your help. I said, fine, I'll be very happy to help. So I said, how many complaints do you have? They said, a few. I said, how many? Maybe 500,000. I said, well, let's start working with it. So I got the data and I started analyzing it. So basically they have done a great job of keeping the data, some data in tabular format, other was unstructured data. And in that case, tabular data was when the complaint arrived, who received it, what was the type of the complaint, was it resolved, whose fault was it. And the unstructured part of it was the exchange of emails and faxes. So imagine looking at 500,000 exchanges of emails and trying to get some answer from it. So I started working with it, and the first thing I wanted to know is why would people complain, and is there a pattern? Are there some days where there are more complaints than others? And I looked at the data and I analyzed it in all different formats, and I couldn't find what the impetus for complaints being higher on a certain day and lower on others. And it continued for maybe a month or so, and then one day I was getting off the bus in Toronto. And I was still thinking about it, and I stepped out without looking at on the ground, and I stepped into a puddle of water, and now I was sort of ankle deep into water, and it was just 1 foot wet and the other dry, and I was extremely annoyed. And I was walking back, and then it hit me, and I said, well, wait a second. Today it rained unexpectedly, and I wasn't prepared for it. That's why I'm wet, and I wasn't looking for it. What if there is a relationship between extreme weather and the type of complaints TTC receives? So I went to the Environment Canada's website and I got data on rain and precipitation, wind and the like. And there I found something very interesting. The 10 most excessive days for complaints, the 10 days where people complained the most, were the days when the weather was bad. It was unexpected rain, an extreme drop in temperature, too much snow, very windy day. So I went back to the TTC's executives and I said, I've got good news and bad news. And so good news is I know why people would complain excessively on certain days. I know the reason for it. The bad news is there's nothing you can do about it.
Organizations can leverage the almost unlimited amount of data now available to them in a growing number of ways. However, all organizations ultimately use data science for the same reason: to discover optimum solutions to existing problems. Let's take a look at 3 examples of data science providing innovative solutions for old problems. In transport, Uber collects real-time user data to discover how many drivers are available, if more are needed, and if they should allow a surge charge to attract more drivers. Uber uses data to put the right number of drivers in the right place at the right time for a cost the rider is willing to pay. In a different transport-related data science effort, the Toronto Transportation Commission has made great strides in solving an old problem with traffic flows, restructuring those flows in and around the city. Using data science tools and analysis, they have gathered data to better understand streetcar operations and identify areas for interventions, analyzed customer complaints data, used probe data to better understand traffic performance on main routes, and created a team to better capitalize on big data for both planning, operations, and evaluation. By focusing on peak hour clearances and identifying the most congested routes, monthly hours lost for commuters due to traffic congestion dropped from 4.75 hours in 2010 to 3 hours in mid-2014. In facing issues in our environment, data science can also play a proactive role. Freshwater lakes supply a variety of human and ecological needs, such as providing drinking water and producing food. But lakes across the world are threatened by increasing incidences of harmful cyanobacterial blooms. There are many projects and studies to solve this long-existing dilemma. In the U.S., a team of scientists from research centers stretching from Maine to South Carolina is developing and deploying high-tech tools to explore cyanobacteria in lakes across the East Coast. The team is using robotic boats, buoys, and camera-equipped drones to measure physical, chemical, and biological data in lakes where cyanobacteria are detected, collecting large volumes of data related to the lakes and the development of the harmful blooms. The project is also building new algorithmic models to assess the findings. The information collected will lead to better predictions of when and where cyanobacterial blooms take place, enabling proactive approaches to protect public health in recreational lakes and in those that supply drinking water. Such interdisciplinary training prepares the next generation of scientists to address societal issues with the proper modernized data science tools. It takes gathering a lot of data, cleaning and preparing it, and then analyzing it to gain the insight needed to develop better solutions for today's enterprises. How do you get a better solution that is efficient? You must identify the problem and establish a clear understanding of it. Gather the data for analysis, identify the right tools to use, and develop a data strategy. Case studies are also helpful in customizing a potential solution. Once these conditions exist and available data is extracted, you can develop a machine learning model. It will take time for an organization to refine best practices for data strategy using data science, but the benefits are worth it.
I really enjoy regression. I'd say regression was maybe one of the first concepts that really helped me understand data, so I enjoy regression.
I really like data visualization. I think it's a key element for people to get across their message to people that don't understand that well what data science is.
Artificial neural networks.
I'm really passionate about neural networks because we have a lot to learn with nature. So when we are trying to mimic our brain, I think that we can do some applications with this behavior, this biological behavior in algorithms.
Data visualization with R, I love to do this.
Nearest neighbor. It's the simplest, but it just gets the best results so many more times than some overblown, overworked algorithm that's just as likely to overfit as it is to make a good fit.
So structured data is more like tabular data, things that you're familiar with in Microsoft Excel format. You've got rows and columns, and that's called structured data. Unstructured data is basically data that is coming from mostly from web, where it's not tabular. It's not in rows and columns, it's text, sometimes it's video and audio. So you would have to deploy more sophisticated algorithms to extract data. And in fact, a lot of times we take unstructured data and spend a great deal of time and effort to get some structure out of it and then analyze it. So if you have something which fits nicely into tables and columns and rows, go ahead, that's your structured data. But if you see if it's a weblog, or if you're trying to get information out of web pages and you've got a gazillion web pages, that's unstructured data that would require a little bit more effort to get the information out of it. There are thousands of books written on regression and millions of lectures delivered on regression, and I always feel that they don't do a good job of explaining regression because they get into data and models and statistical distributions. Let's forget about it. Let me explain regression in the simplest possible terms. If you have ever taken a cab ride, a taxi ride, you understand regression. Here's how it works. The moment you sit in a cab, you see that there's a fixed amount there. It says $2.50. Whether the cab moves or you get off, this is what you owe to the driver. The moment you step into a cab, that's a constant. You have to pay that amount if you have stepped into a cab. Then as it starts moving, for every meter or 100 meters, the fare increases by a certain amount. So there's a fraction, there's a relationship between distance and the amount you would pay above and beyond that constant. And if you're not moving and you're stuck in traffic, then every additional minute you have to pay more. So as the minutes increase, your fare increases. As the distance increases, your fare increases. And while all this is happening, you've already paid a base fare, which is the constant. This is what regression is. Regression tells you what the base fare is and what is the relationship between time and the fare you have paid and the distance you've traveled and the fare you've paid. Because in the absence of knowing those relationships and just knowing how much people traveled for and how much they paid, regression allows you to compute that constant that you didn't know it was 250, and it would compute the relationship between the fare and the distance and the fare and the time. That's a regression. Cloud it's a godsend for data scientists, primarily because you're able to take you take your data, take your information and put it in the cloud, put it in a central storage system. It allows you to bypass the physical limitations of the computers and the systems you're using, and it allows you to deploy the analytics and storage capacities of advanced machines that do not necessarily have to be your machine or your company's machine. Cloud allows you not just to store large amounts of data on servers somewhere in California or in Nevada, but it also allows you to deploy very advanced computing algorithms and the ability to do high performance computing using machines that are not yours. So think of it as you have some information, you can't store it, so you send it to storage space, let's call it cloud, and the algorithms that you need to use, you don't have them with you, but then on the cloud, you have those algorithms available. So what you do is you deploy those algorithms on very large data sets, and you're able to do it even though your own systems, your own machines, your own computing environments were not allowing you to do so. So cloud is beautiful. And the other thing cloud is beautiful for is that it allows multiple entities to work with same data at the same time. So you can be working with the same data that your colleagues in, say, Germany, and another team in India, and another team in Ghana, they are collectively working, and they are able to do so because the information and the algorithms and the tools and the answers and the results, whatever they needed, is available at a central place, which we call cloud. So cloud is beautiful.
Using the cloud enables you to get instant access to open source technologies like Apache Spark without the need to install and configure them locally. Using the cloud also gives you access to the most up-to-date tools and libraries without the worry of maintaining them and ensuring that they are up to date. The cloud is accessible from everywhere and in every time zone. You can use cloud-based technologies from your laptop, from your tablet, and even from your phone, enabling collaboration more easily than ever before. Multiple collaborators or teams can access the data simultaneously, working together on producing a solution. Some big tech companies offer cloud platforms, allowing you to become familiar with cloud-based technologies in a pre-built environment. IBM offers the IBM Cloud, Amazon offers Amazon Web Services or AWS, and Google offers Google Cloud Platform. IBM also provides Skills Network Labs or SN Labs to learners register to any of the learning portals on the IBM Developer Skills Network, where you have access to tools like Jupyter Notebooks and Spark clusters, so you can create your own data science project and develop solutions. With practice and familiarity, you will discover how the cloud dramatically enhances productivity for data scientists. In this digital world, everyone leaves a trace. From our travel habits to our workouts and entertainment, the increasing number of internet-connected devices that we interact with on a daily basis record vast amounts of data about us. There's even a name for it: big data. Ernst & Young offers the following definition. Big data refers to the dynamic, large, and disparate volumes of data being created by people, tools, and machines. It requires new, innovative, and scalable technology to collect, host, and analytically process the vast amount of data gathered in order to derive real-time business insights that relate to consumers, risk, profit, performance, productivity management, and enhanced shareholder value. There is no one definition of big data, but there are certain elements that are common across the different definitions, such as velocity, volume, variety, veracity, and value. These are the V's of big data. Velocity is the speed at which data accumulates. Data is being generated extremely fast in a process that never stops. Near or real-time streaming, local, and cloud-based technologies can process information very quickly. Volume is the scale of the data, or the increase in the amount of data stored. Drivers of volume are the increase in data sources, higher resolution sensors, and scalable infrastructure. Variety is the diversity of the data. Structured data fits neatly into rows and columns in relational databases, while unstructured data is not organized in a predefined way, like tweets, blog posts, pictures, numbers, and video. Variety also reflects that data comes from different sources, machines, people, and processes, both internal and external to organizations. Drivers are mobile technologies, social media, wearable technologies, geotechnologies, video, and many, many more. Veracity is the quality and origin of data and its conformity to facts and accuracy. Attributes include consistency, completeness, integrity, and ambiguity. Drivers include cost and the need for traceability. With the large amount of data available, the debate rages on about the accuracy of data in the digital age. Is the information real or is it false? Value is our ability and need to turn data into value. Value isn't just profit. It may have medical or social benefits, as well as customer, employee, or personal satisfaction. The main reason that people invest time to understand big data is to derive value from it. Let's look at some examples of the V's in action. Velocity. Every 60 seconds, hours of footage are uploaded to YouTube, which is generating data. Think about how quickly data accumulates over hours, days, and years. Volume. The world population is approximately 7 billion people, and the vast majority are now using digital devices, mobile phones, desktop and laptop computers, wearable devices, and so on. These devices all generate, capture, and store data, approximately 2.5 quintillion bytes every day. That's the equivalent of 10 million Blu-ray DVDs. Variety. Let's think about the different types of data: text, pictures, film, sound, health data from wearable devices, and many different types of data from devices connected to the Internet of Things. Veracity. 80% of data is considered to be unstructured, and we must devise ways to produce reliable and accurate insights. The data must be categorized, analyzed, and visualized. Data scientists today derive insights from big data and cope with the challenges that these massive data sets present. The scale of the data being collected means that it's not feasible to use conventional data analysis tools. However, alternative tools that leverage distributed computing power can overcome this problem. Tools such as Apache Spark, Hadoop, and its ecosystem provides ways to extract, load, analyze, and process the data across distributed compute resources, providing new insights and knowledge. This gives organizations more ways to connect with their customers and enrich the services they offer. So next time you strap on your smartwatch, unlock your smartphone, or track your workout, remember your data is starting a journey that might take it all the way around the world through big data analysis and back to you.
Traditionally, in computation and processing data, we would bring the data to the computer. You'd run a program and you'd bring the data into the program. In a big data cluster, what Larry Page and Sergey Brin came up with, this pretty simple, is they took the data and they sliced it into pieces, and they distributed each, and they replicated each piece or triplicated each piece, and they would send it, the pieces of these files, to thousands of computers. First it was hundreds, but then now it's thousands, now it's tens of thousands. And then they would send the same program to all these computers in the cluster. And each computer would run the program on its little piece of the file and send the results back. The results would then be sorted, and those results would then be redistributed back to another process. The first process is called a map or a mapper process, and the second one was called a reduce process. Fairly simple concepts, but it turned out that you could do lots and lots of different kinds of, handle lots and lots of different kinds of problems in very, very, very large data sets. So the one thing that's nice about these big data clusters is they scale linearly. You add twice as many servers and you get twice the performance, and you can handle twice the amount of data. So this was just broke a bottleneck for all the major social media companies. Yahoo then got on board. Yahoo hired someone named Doug Cutting, who had been working on a clone or a copy of the Google big data architecture, and that's now called Hadoop. And if you Google Hadoop, you'll see that it's a now very popular term. And there are many, 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 if you look at the big data ecology, there are hundreds, if not thousands, of companies out there that have some kind of footprint in the big data world. Most of the components of data science have been around for many, 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 many decades, but they're all coming together now with some new nuances, I guess. At the bottom of data science, you see probability and statistics. You see algebra, linear algebra. You see programming, and you see databases. They've all been here. But what's happened now is we now have the computational capabilities to apply some new techniques, machine learning, where now we can take really large data sets, and instead of taking a sample and trying to test some hypothesis, we can take really, really large data sets and look for patterns. And so back off one level from hypothesis testing to finding patterns that maybe will generate hypotheses. Now this can bother some very traditional statisticians and gets them really annoyed sometimes that you're supposed to have a hypothesis that is independent of the data, and then you test it. So once some of these machine learning techniques started, were really the only way you could analyze some of these really large social media data sets. So what we've seen is that the combination of traditional traditional areas, computer science, probability, statistics, mathematics, all coming together in this thing that we call decision sciences. Our department at Stern, I'll give a little plug here, we happen to have been very well situated among business schools because we're one of the few business schools that has a real statistics department with real PhD level statisticians in it. We have an operations management department and an information systems department. So we have a wide range of computer scientists to statisticians to operations researchers. And so we were like perfectly positioned, as a couple of other business schools were, to jump onto this bandwagon and say, okay, this is decision sciences. And Foster Provo, who's in my department, was the first director of the NYU Center for Data Science. 4 years ago, maybe 5 years ago. I mean, this is one of those cases where you can just go to Google and search for data science and see how often it occurred, and you'll see almost nothing, and then just a spike. The same thing you would see with big data about 7 or 8 years ago. So data science is a term I hadn't heard of probably 5 years ago. The first question is, what is it? And I think faculty and everybody's still trying to get their hands around exactly what is business analytics and what is data science. We certainly know the components of it, but it's morphing and changing and growing. I mean, in the last 3 years, deep learning has just been added into the mix. Neural networks have been around for 20 or 30 years. 20 years ago, I would teach neural networks in a class, and you really couldn't do very much with them. And now, some researchers have come up with multi-layer neural networks in Toronto, in particular, at the University of Toronto. And that technology is now rapidly expanding. It's being used by Google, by Facebook, by lots of companies.
Digital transformation affects business operations, updating existing processes and operations and creating new ones to harness the benefits of new technologies. This digital change integrates digital technology into all areas of an organization, resulting in fundamental changes to how it operates and delivers value to customers. It is an organizational and cultural change driven by data science and especially big data. The availability of vast amounts of data and the competitive advantage that analyzing it brings has triggered digital transformations throughout many industries. Netflix moved from being a postal DVD lending system to one of the world's foremost video streaming providers. The Houston Rockets NBA team used data gathered by overhead cameras to analyze the most productive plays, and Lufthansa analyzed customer data to improve its service. Organizations all around us are changing to their very core. Let's take a look at an example to see how big data can trigger a digital transformation, not just in one organization, but in an entire industry. In 2018, the Houston Rockets, a National Basketball Association, or NBA team, raised their game using big data. The Rockets were one of 4 NBA teams to install a video tracking system which mined raw data from games. They analyzed video tracking data to investigate which plays provided the best opportunities for high scores, and discovered something surprising. Data analysis revealed that the shots that provide the best opportunities for high scores are 2-point dunks from inside the 2-point zone and 3-point shots from outside the 3-point line, not long-range 2-point shots from inside it. This discovery entirely changed the way the team approached each game, increasing the number of 3-point shots attempted. In the 2017-18 season, the Rockets made more 3-point shots than any other team in NBA history, and this was a major reason they won more games than any of their rivals. In basketball, big data changed the way teams try to win, transforming the approach to the game. Digital transformation is not simply duplicating existing processes in digital form. The in-depth analysis of how the business operates helps organizations discover how to improve their processes and operations, and harness the benefits of integrating data science into their workflows. Most organizations realize that digital transformation will require fundamental changes to their approach towards data, employees, and customers, and it will affect the organizational culture. Digital transformation impacts every aspect of the organization, so it is handled by decision makers at the very top levels to ensure success. The support of the Chief Executive Officer is crucial to the digital transformation process, as is the support of the Chief Information Officer and the emerging role of Chief Data Officer. But they also require support from the executives who control budgets, personnel decisions, and day-to-day priorities. This is a whole organization process. Everyone must support it for it to succeed. There is no doubt dealing with all the issues that arise in this effort requires a new mindset, but digital transformation is the way to succeed now and in the future.
Norman White. I'm a clinical faculty member in the IOMS department, Information Operations and Management Science department here at Stern. I've been here for a long time, since I got out of college pretty much. I'm sort of a techie, geeky kind of person. I really like to play with technology in my spare time. I'm currently faculty director of the Stern Center for Research Computing, in which we have a private cloud that runs lots of different kinds of systems. Many of our faculty or PhD students who need specialized hardware and software will come to us. We'll spin up a machine for them, configure it, help them and advise on them. And a lot of the data scientists, or virtually all the data scientists at Stern, use our facilities, and their PhD students use them a lot. I have an undergraduate degree in applied physics, and while I was an undergrad, I took a number of economics courses. So I ended up deciding to go to business school, but I had, this was in the early days of computers, and I had gotten interested in computers. And I came to Stern, which was then NYU Business School downtown, and they had a little computer center. And I decided that I was going to learn two things while I was there. One, I was going to learn how to program. I'd taken one programming course in college. And I was going to learn how to touch type. I never did learn how to touch type. Oh, I did, maybe I did, but I forgot. Now I'm back to two-finger pecking. But I became a self-taught programmer, and then I took a number of courses at IBM, because I eventually became the director of the computer center while I was getting my PhD in economics and statistics at Stern. So in 1973, the school formed a department called Computer Applications and Information Systems, and I was one of the first faculty members in the department, and I've been here ever since. So my typical Monday is I usually get in around 11 o'clock, and I do my email at home first, but I come in, and I have two classes on Monday. I have a class on design and development of web-based systems at 6 o'clock. 2 o'clock, I have a dealing with data class. The class is based all on Python notebooks. So we start with sort of the basics of Unix and Linux, just to get the students used to that. We move on to some Python, some regular expressions, a lot of relational databases, some Python pandas, which is sort of like R for Python. Lets you do mathematical and statistical calculations in Python. And then I end up with big data, for which, as you probably know, I'm an evangelist. And the students have weekly homeworks. I put them in teams, and they have to do a big project at the end of the term. And they do some really cool things. Yes, in fact, the whole course is taught using Jupyter Notebooks. Every student has their own virtual machine on Amazon Web Services. So we pre-configure all the machines, and they get a standard image that has all of the materials for the course, either loaded on it, or in a Jupyter Notebook, there are the commands to download it or update the server with the right software. So everybody's in the same environment. It doesn't matter whether they have a Mac or a Windows machine or how old it is. Everybody can do everything in the class. Everybody knows how to program at least a little bit. They all have a little bit of programming background at least. And some of them have a lot. Some of them are Masters of Science in Computer Science. Some of them are MBA students who've come in from technical fields and programmed every day. and others are ones who maybe took a programming course in college 4 or 5 years ago, but at least they can think computationally, and that which I think is the most important thing that they need. Data science and business analytics have become very hot subjects in the last 4 or 5 years. We have new tools, we have new approaches, and we have lots and lots of data that traditional techniques just couldn't really store and handle. And I think the word is out. I think at this point, at first, companies and employers understood the need, especially in certain fields. I can remember talking to a major bank 3 years ago about big data, and there was one little group in the bank where one person had a little effort and put a little cluster together. Now that same bank has 5 or 6 major big data clusters, and they're putting all of their credit card data in it, and they're grinding it upside down and sideways, using all sorts of data science kinds of techniques. 2 years ago, or was it last year, I think, our undergraduate dealing with data course had 28 students in it. This year, it has 140. So that means that the parents are now beginning to get the word, because one thing we understand with our undergrads is the parents who are paying very hefty tuitions, they tell their sons and daughters, you should be an accountant, right? Or you should go into financial services or into marketing, because this is where the money is. Now they're getting the word that maybe you should take some more sort of STEM classes in high school and be ready to go into data science or go into fields where analytics is just playing more and more, has become more and more important. It depends on who you are. I have my own definition of big data. My definition of big data is data that is large enough and has enough volume and velocity that you cannot handle it with traditional database systems. Some of our statisticians think big data is something you can't fit on a thumb drive. Big data, to me, it was started by Google. When Google tried to figure out how they were, when Larry Page and Sergey Brin wanted to basically figure out how to solve their PageRank algorithm, there was nothing out there. They were trying to store all of the web pages in the world, and there was no technology, there was no way to do this, and so they went out and developed this approach, which is now Hadoop has copied it, but this is where all these large big data clusters are found. But big data has now also expanded into how do you analyze. There are new analytical techniques and statistical techniques for handling these really, really, really large data sets. We'll probably get to deep learning at some point along here. But
in data science, there are many terms that are used interchangeably, so let's explore the most common ones. The term big data refers to data sets that are so massive, so quickly built, and so varied that they defy traditional analysis methods, such as you might perform with a relational database. The concurrent development of enormous compute power in distributed networks and new tools and techniques for data analysis means that organizations now have the power to analyze these vast data sets, and new knowledge and insights are becoming available to everyone. Big data is often described in terms of 5 V's: velocity, volume, variety, veracity, and value. Data mining is the process of automatically searching and analyzing data, discovering previously unrevealed patterns. It involves pre-processing the data to prepare it and transforming it into an appropriate format. Once this is done, insights and patterns are mined and extracted using various tools and techniques ranging from simple data visualization tools to machine learning and statistical models. Machine learning is a subset of AI that uses computer algorithms to analyze data and make intelligent decisions based on what it has learned without being explicitly programmed. Machine learning algorithms are trained with large sets of data, and they learn from examples. They do not follow rules-based algorithms. Machine learning is what enables machines to solve problems on their own and make accurate predictions using the provided data. Deep learning is a specialized subset of machine learning that uses layered neural networks to simulate human decision-making. Deep learning algorithms can label and categorize information and identify patterns. It is what enables AI systems to continuously learn on the job and improve the quality and accuracy of results by determining whether decisions were correct. Artificial neural networks, often referred to simply as neural networks, take inspiration from biological neural networks, although they work quite a bit differently. A neural network in AI is a collection of small computing units called neurons that take incoming data and learn to make decisions over time. Neural networks are often layered deep and are the reason deep learning algorithms become more efficient as the datasets increase in volume, as opposed to other machine learning algorithms that may plateau as data increases. Now that you have a broad understanding of the differences between some key AI concepts, there is one more differentiation that is important to understand, that between artificial intelligence and data science. Data science is the process and method for extracting knowledge and insights from large volumes of disparate data. It's an interdisciplinary field involving mathematics, statistical analysis, data visualization, machine learning, and more. It's what makes it possible for us to appropriate information, see patterns, find meaning from large volumes of data, and use it to make decisions that drive business. Data science can use many of the AI techniques to derive insight from data. For example, it could use machine learning algorithms and even deep learning models to extract meaning and draw inferences from data. There is some interaction between AI and data science, but one is not a subset of the other. Rather, data science is a broad term that encompasses the entire data processing methodology, while AI includes everything that allows computers to learn how to solve problems and make intelligent decisions. Both AI and data science can involve the use of big data, that is, significantly large volumes of data.
I guess computer science's attempt to mimic the neurons and how our brain actually functions. So 20, 30 years ago, a neural network would have some inputs that would come in. They would be fed into different processing nodes that would then do some transformation on them and aggregate them or something, and then maybe go to another level of nodes. And finally, some output would come out. And I can remember training a neural network to recognize digits, handwritten digits and stuff. So a neural network is trying to use a computer program that will mimic how our brains use neurons to process things, neurons to synapses, and building these complex networks that can be trained. So a neural network starts out with some inputs and some outputs, and you keep feeding these inputs in to try to see what kinds of transformations will get to these outputs. And you keep doing this over and over and over again in a way that this network should converge, so the transformations will eventually get these outputs. Problem with neural networks was that even though the theory was there, and they did work on small problems, like recognizing handwritten digits and things like that, they were computationally very intensive. And so they went out of favor, and I stopped teaching them, probably 15 years ago. And then, all of a sudden, you started hearing about deep learning. I heard the term deep learning. This is another term that when did you first hear it? 4 years ago, 5 years ago? And so I finally said, what the hell is deep learning? It's really doing all this great stuff. What is it? And I Googled it and I thought, well, this is neural networks on steroids. What they did was they just had more multiple layers of neural networks, and they used lots and lots and lots of computing power to solve them. Just before this interview, I had a young faculty member in the marketing department whose research is partially based on deep learning. And so she needs a computer that has a graphics processing unit in it, because it takes an enormous amount of matrix and linear algebra calculations to actually do all of the mathematics that you need in neural networks. But they are now quite capable. We now have neural networks and deep learning that can recognize speech, can recognize people. If you're out there, and getting your face recognized, I guarantee that NSA has a lot of work going on in neural networks. The university right now, as director of research computing, I have a small set of machines down at our South Data Center. And I went in there last week, and there were just piles and piles and piles of cardboard boxes, all from Dell with a GPU on the side. Well, the GPU is a graphics processing unit. There's only one application in this university that needs 200 servers, each with graphics processing units in it, and each graphics processing unit has the equivalent of 600 cores of processing. So this is tens of thousands of processing cores. That is for deep learning, I guarantee. Some of the first ones are speech recognition. Jan LeCun, who teaches the deep learning class at NYU and is also the head data scientist at Facebook, comes into class with a notebook, and it's a pretty thick notebook. It looks a little odd because it's like this, and it's that thick because it has a couple of graphics processing units in it. And then he will ask the class to start to speak to this thing, and it will train while he's in class. He will train a neural network to recognize speech. So recognizing speech, recognizing people, images, classifying images, almost all of the traditional tasks that neural nets used to work on in little tiny things, now they can do really, really, really large things. It will learn on its own the difference between a cat and a dog and different kinds of objects. It doesn't have to be taught. It just learns. That's why they call it deep learning. And if you hear, he plays this, if you hear how it recognizes speech and generates speech, it sounds like a baby learning to talk. Right? You're like, all of a sudden this stupid machine is talking to you and learned how to talk. That's cool. You need to learn some linear algebra. A lot of this stuff is based on matrix and linear algebra, so you need to know how to use linear algebra to do transformations. Now, on the other hand, there's now lots of packages out there that will do deep learning, and they'll do all the linear algebra for you, but you should have some idea of what is happening underneath. The deep learning in particular needs really high-powered computational power. So it's not something that you're going to go out and do on your notebook, or you could play with it, but if you really want to do it seriously, you have to have some special computational resources. Everybody now deals with machine learning, but recommender systems are certainly one of the major applications. Classifications, cluster analysis, trying to find some of the marketing questions from 20 years ago, market basket analysis, what goods tend to be bought together. That was computationally a very difficult problem. I mean, we're now doing that all the time with machine learning. So predictive analytics is another area of machine learning where we're using new techniques to predict things that statisticians don't particularly like. Decision trees, Bayesian analysis, naive Bayes, lots of different techniques. The nice thing about them is that in packages like R now, you really have to understand how these techniques can be used, and you don't have to know exactly how to do them, but you have to understand what their meanings are. Precision versus recall, and how, the problems of oversampling and overfitting. So you can, someone who knows a little bit about data science can apply these techniques, but they really need to know maybe not the details of the technique as much as how, what the trade-offs are.
So some applications of machine learning in FinTech are probably a couple of different things I can talk about there. One of them is recommendations, right? So when you use Netflix or you use Facebook or a lot of different software services, the recommendations are served to you, meaning, hey, you're a user, you've watched this show, so maybe you'd like to see this other show, right? Or you follow this person, so maybe you should follow that other person. It's actually kind of the same thing in FinTech, right? Because you've looked at, if you're an investment professional, right? And because you've looked at this investment idea, it might be really cool for you to look at this other investment idea, which is kind of similar, right? It's a similar kind of asset, or it's a similar kind of company, or it's a similar kind of technique for doing the investment. So we can apply recommendations using machine learning throughout a lot of different parts of FinTech. Another one that people talk about and is important, especially on retail, in the retail aspects of banking and finance, is fraud detection. Trying to determine whether a charge that comes through a credit card is fraudulent or not in real time is a machine learning problem, right? You have to learn from all of the transactions that have happened previously and build a model. And when the charge comes through, you have to compute all this stuff and say, yeah, we think that's okay, or that's not so good. Let's route it to, our fraud people to kind of check.
Data science techniques to understand and analyze the large data sets available today has a huge impact on human lives. It can provide targeted information to help healthcare professionals give the best treatment to patients, or help predict natural disasters so that people can prepare early, and much more besides. In healthcare, data scientists use predictive analytics developed from data mining, data modeling, statistics, and machine learning to find the best options for patients. This type of predictive analytics examines all known factors for a disease, including gene markers, associated conditions, and environmental factors. It then recommends appropriate tests, suitable trials, and any suggested treatments. Every individual physician has their own store of knowledge gained from their studies, interests, and experiences. Data science systems that use predictive analytics ensure that all physicians can also access the latest information about the disease, tests, and treatment plans tailored to their specific patient. With this type of system, every physician has access to the same knowledge, and the best options can be consistently offered, improving patient outcomes. For example, a study by the Boston Consulting Group and AdvaMed DX, an industry association of medical diagnostics companies, examined the barriers to the adoption of potentially life-saving diagnostic tests for patients with a specific cancer and a particular gene marker. The study discovered that the biggest factor in the patient being offered a specific test was the patient's oncologist, who may or may not have known about the test and its relationship to the gene marker. By providing extra information through data science tools, physicians can be made aware of the most helpful tests and treatments for a specific patient. There are many opportunities to explore other ways to mine data, such as from electronic medical records for different types of medical research. Schools such as the North Shore University Health System in suburban Chicago, a leader in the implementation of electronic medical records, EMR systems, now offer guidance on data mining. It is the first healthcare provider in America to be awarded the highest level of EMR deployment for both inpatient and outpatient care. This remarkable effort has generated much anonymized data available for innovative analytics research. Developing more sophisticated big data analytics capabilities helps healthcare organizations move from basic descriptive analytics towards predictive insights thanks to data science. In the field of disaster preparedness, the ability to save lives using data science tools has been under development for many years. The use of predictive analytics tools is improving and providing new data analysis in a multitude of ways, alerting populations to danger faster than ever before. Large, high-quality datasets can be used to predict the occurrence of numerous types of natural disasters, which can be the difference between life and death for thousands of people. Earthquakes, hurricanes and tornadoes, floods, and volcanic eruptions can be predicted with the help of data science. Recent research at the University of Warwick in the UK used social media content such as photos and keywords to track the development of floods, hurricanes, and other weather events. When added to the information recorded by scientists and weather stations, this type of data can be used to improve the predictions for localized weather events. Because the real benefit of this knowledge is so important, schools are starting to include this type of data science education in their curriculum. For instance, the University of Chicago Graham School offers a Master of Science course in Threat and Response Management. Data science tools enable organizations to analyze vast quantities of data from widely different sources and present that information in a way that allows data scientists to gain new knowledge, in some cases, saving hundreds of lives.
At the end of the day, for businesses, they know one thing, that if they are unable to measure something, they are unable to improve it. And if they are unable to measure their costs, they are unable to reduce them. If they are unable to measure their profits, they are unable to increase them. So the first thing a company has to do is to start recording information, start capturing data. Data about costs, data about and then differentiated by labor costs and material costs, the cost to how much it costs to sell one product and the total cost, and then you look at the revenue. Where is your revenue coming from? Is your 80% of your revenue coming from 20% of your customers, or is it the other way around? So first thing first, start capturing data. Once you have data, then you can apply algorithms and analytics to it. So the first thing to do would be to capture data. If you're not capturing it, start capturing it. If you're capturing it, archive it. Do not overwrite on your old data thinking you don't need it anymore. Data never gets old. Data is always relevant, even if it's 100 years old, 200 years old. It is relevant to you and your firm and your success. So keep data, capture it, archive it, make sure nothing goes to waste, make sure there's a consistency, so someone 20 years later trying to understand that data should be able to do so. So have proper documentation, do it now, put the best practices for data archiving in place the moment you start a business. And if you're already in business and you haven't done it, do it now.
Start measuring things. Too many companies haven't measured things properly for a decade, and then they decide they want data science. Data science and inside a company is only going to be as valuable as the data collected. Garbage in, garbage out is a rule in any sort of analysis.
If something is not measured, it's very difficult to improve it or to change it. So the very first step is measurement. If companies have existing data, then they should start looking at it and cleaning it. If they don't have existing data, then they need to start collecting it.
I think to look for a team who love to work as a data scientist.
I think that the first step is to have employees that they are interested on data science, because if you don't have interest in your company, you will not have like engagement.
Companies should remember that it's key to have a team, so it's not one data scientist, but a team of them that each of them have strengths in different areas of data science.
And big data are making an undeniable impact on businesses, changing day-to-day operations, financial analytics, and especially interactions with customers. It's clear that businesses can gain enormous value from the insights data science can provide, but sometimes it's hard to see exactly how. So let's look at some examples. In this era of big data, almost everyone generates masses of data every day, often without being aware of it. This digital trace reveals the patterns of our online lives. If you have ever searched for or bought a product on a site like Amazon, you will notice that it starts making recommendations related to your search. This type of system, known as a recommendation engine, is a common application of data science. Companies like Amazon, Netflix, and Spotify use algorithms to make specific recommendations derived from customer preferences and historical behavior. Personal assistants like Siri on Apple devices use data science to devise answers to the infinite number of questions end users may ask. Google watches your every move in the world, your online shopping habits, and your social media. Then it analyzes that data to create recommendations for restaurants, bars, shops, and other attractions based on the data collected from your device and your current location. Wearable devices like Fitbits, Apple Watches, and Android watches add information about your activity levels, sleep patterns, and heart rate to the data you generate. Now that we know how consumers generate data, let's take a look at how data science is impacting business. In 2011, McKinsey & Company said that data science was going to become the key basis of competition, supporting new waves of productivity, growth, and innovation. In 2013, UPS announced that it was using data from customers, drivers, and vehicles in a new route guidance system aimed to save time, money, and fuel. Initiatives like this support the statement that data science will fundamentally change the way businesses compete and operate. How does a firm gain a competitive advantage? Let's take Netflix as an example. Netflix collects and analyzes massive amounts of data from millions of users, including which shows people are watching at what time of day, when people pause, rewind, and fast forward, and which shows, directors, and actors they search for. Netflix can be confident that a show will be a hit before filming even begins by analyzing users' preference for certain directors and acting talent, and discovering which combinations people enjoy. Add this to the success of earlier versions of a show, and you have a hit. For example, Netflix knew many of its users had streamed the work of David Fincher. They also knew that films featuring Robin Wright had always done well, and that the British version of House of Cards was very successful. Netflix knew that significant numbers of people who liked Fincher also liked Wright. All this information combined to suggest that buying the series would be a good investment for the company. They were right, it was a huge hit. Thanks to data science, Netflix knows what people want before they do.
Scientists, the high-end data scientists are mostly PhDs. They often come out of physics, out of statistics. They have to have computer science background, they have to have a math background, they have to know about databases and statistics and probability and all that stuff. However, if you're coming into a data science team, I think that the first skills you need is you need to know how to program, at least have some computational thinking. So you've had to have taken a programming course. You need to know some algebra, at least up to analytics geometry, and hopefully some calculus. Some basic probability, some basic statistics. I mean, you really have to understand statistical inference and different statistical distributions, and database. I mean, one of the easiest places to start is relational databases, which stores lots and lots of our data. So people can first walk before they can run by at least understanding about computers and databases and how we store things. And if you understand relational databases, nowadays you can still, just with that understanding, use big data clusters as if they were just a big relational database. You don't have to really understand the whole MapReduce programming model. But then, as you go further up in the field, then you have to know a lot of computer science theory and statistics. It's really, and probability. It's really the intersection of them that the high-end data scientists, the PhD data scientists, work with. I do a lot of self-learning. I think everybody these days, I mean, I learned about Hadoop all by myself. I read some articles, I watched some videos, I thought, I played. Although I'm a builder, I'm a tinkerer. So when I really want to, if I want to figure out how to do something, I build it. I mean, my first HPC cluster, I'd heard about this term, a Beowulf cluster. And again, I'm like, what the hell's that? So I looked it up and said, oh, that's just a bunch of computers hooked together with a TCP/IP network. That's pretty easy. So we got a grant from Citibank, and we built a five-thing cluster. And I said, oh, well, that's HPC. So I had one of the first HPC clusters at the university. It was tiny, but a lot of our researchers loved it because they could run stuff 40 and 50 times faster. So I think one of the ways you learn things is you do them. You have to do them. And these online learning platforms, especially now that we have things like IPython and Jupyter Notebooks and I guess Zeppelin, means that you can actually go in and take some of these courses and you can do things right then. And you can see them and feel them and play with them. And at that point, you know, you start to get your head around what is actually happening. Motivation is the key problem in all of these, is how to keep people motivated and how, and I think the badge system that that the Big Data University has is one of the ways. Is how do you get people to keep going through? But if they want to, they can't. Right? It's up to the individual too. So they have to understand what the goal is. The place it can't sit is probably under the CIO, the Chief Information Officer. CIOs, current Chief Information Officers in many companies, got there from an accounting background or a finance background. They're clueless. Sorry, but I mean, they really, it has to come out of the research side, right? So you'll find data scientists primarily in companies that have some research agenda, pharmaceuticals, finance, all of any technology company. And if you look at, we can't keep some of our PhD data scientists in our program. They're now at Facebook, they're at LinkedIn, they're at Uber, they're at Lyft, because the demand out there for the PhD level data scientists is just unbelievable. They make large amounts of money and they're playing with problems that are really, really neat. Like, you know, how do you schedule the Uber cars? Right? And you have enormous amounts.
Companies are hiring people for a data science team, may it be a data scientist or an analyst, or a chief data scientist, the tendency would be to find the person who has all the skills, that they know the domain-specific knowledge, they're excellent in analyzing structured and unstructured data, and they're great at presenting, and they've got the great storytelling skills. So if you put all this together, you will realize you're looking for a unicorn, and your odds of finding a unicorn are pretty rare. I think what you need to do is to see, given the pool of applicants you have, who has the most resonance with your firm's DNA. Because see, you can teach analytic skills. Anyone can learn analytic skills if they would dedicate time and effort to it. But what really matters is who is passionate about the kind of business that you do. Someone could be a great data scientist in a retail environment, but they may not be that excited about working in IT related firms or working with gigabytes of weblogs. But if someone is excited about those weblogs, or someone is excited about health related data, then they would be able to contribute to your productivity much more so. And I would say, if I'm looking for someone, if I have to put together a data science team, I would first look for curiosity. Is that person curious about things, not just for data science, but anything? Like, are they curious about why this room is painted the certain way, why the bookshelves have books, and what kind of books? They have to have certain degree of curiosity about everything that is in their vision, that they look at. The second thing is, do they have a sense of humor? Because you see, you have to have a lighthearted about it. If someone is too serious about it, they probably would take it too seriously and would not be able to look at the lighter elements. The third thing, I think, and I think the last thing that I would look for, if I have to have a hierarchy, the last thing I would look for are technical skills. I would go through these social skills, curiosity, sense of humor, the ability to tell a story, the ability to know that there is a story there. And then once all is there, then I will say, well, can you do the technical side of it? And if there's some hope or some sign of some technical skills, I would take them, because I can train them in whatever skills they need. But I cannot teach curiosity, I cannot teach storytelling, I cannot certainly instill sense of humor in anyone.
I think there's no hard and fast rule for hiring data scientists. I think it's going to be a case-by-case thing. I would say there has to be some sort of technical component. Somebody should be able to work with and manipulate the data. They should be able to communicate what they find in the data. I find quite often nobody really cares about the R-squared or the confidence interval, so you have to be able to introduce those things and explain something in a compelling way. And they also have to find somebody who is relatable, because data science, it being typically new, means that the person in that role has to make relationships and they have to work across different departments.
If these data scientist has a good mathematics and statistics background,
they have to consider like problem-solving abilities and analysis. A data scientist needs to be good in analyzing problems.
The persons they are hiring, they should love to play with data, and then they know how to play with the data visualization. They have analytical thinking.
When a company is hiring anyone to work on a data science team, they need to think about what role that person is going to take. Before a company begins, they need to understand what they want out of their data science team, and then they need a hire to begin it. As they grow a data science team, they need to understand whether they need engineers, architects, designers to work on visualization, or whether they just need more people who can multiply large matrices.
From a skills point of view, let's focus on the technical skills. And in that case, first thing would be, what kind of a technical platform would you like to adopt? Let's say you want to work in a structured data environment, and let's say you want to work in market research. Then the type of skills you need are slightly different than someone who would like to work in big data environments. If you want to work in the traditional market research data, structured data environment, your skills should be some statistical knowledge, some knowledge of basic statistical algorithms, maybe some machine learning algorithms, and these are the tools that you would like to develop. If you want to work in big data, then there's the other aspect of it, and that is to be able to store data. So you start with the expertise in storing large amounts of data, and then you look into platforms that allow you to do that. The next step would be to be able to manipulate large amounts of data, and the final step would be to apply algorithms to those large sets of data. So it's a three-step process, but most likely it starts, most importantly, it starts with where you would like to be, in what field, in what domain. So in terms of platforms, let's say you want to be in a traditional predictive analytics environment, and you're not working with big data, then R or Stata or Python would be your tools. If you're working mostly with unstructured data, then Python is more suitable than R. If you're working with big data, then Hadoop and Spark are the environments that you would be working with. So it all depends upon where you would like to be and what kind of work excites you, and then you pick your tools. In addition to technical skills, the second aspect of the data science is to have the ability to communicate, the communication skills or presentation skills. I call them storytelling skills. That is, that you have your analysis done. Now, can you tell a great story from it? If you have a very large table, can you synthesize it and make it more appealing, that when it goes on the screen, or is it part of a document that it just speaks, it sings the findings, and the reader just gets it right there. So the ability to present your findings either verbally or in a presentation or in a document. So that communication and presentation skills are equally important as the technical skills are. When you have a great insight and when you're presenting your results, imagine you're driving on a mountain, and then there's a sharp turn, and you can't see what's beyond the turn, and then you make that turn, and then suddenly you see a tremendous valley in front of you, and there's this great sense of awe that I didn't know that, right? So when you present your findings and you have this great finding and you communicate it well, this is what people feel, because they were not expecting it, they were not aware of it, and then this great sense of happiness that now I know. And I didn't know this, now I know. And then it empowers them, it gives them ideas what they can do with this knowledge, this new insight. It's a great sense of joy. And you are able to, as a data scientist, you're able to share it with your clients, because you
Emergence of Internet of Things and advances in distributed computing have brought vast amounts of data and the technological capability to analyze it. Now that we can extract useful insights and new knowledge, we need to know how to shape that data to focus on what to do with it and what it can do for us. Enter data science. Companies like LinkedIn, Glassdoor, Indeed, and Dice track employment trends which show a career in data science moving up the list of most promising jobs to become #1 since 2016. It remains one of the top 3 career choices for 2020. Dice noted that job postings are from companies in a wide variety of industries, not just tech. Global Industry Analysts Incorporated predicts that the data science platform market will grow by $314.8 billion by 2025, driven by a compounded growth of 38.2%. McKinsey Global Institute warned of huge talent shortages for data and analytics by 2018. Forrester research analyst Brandon Purcell said in January of 2019, the demand for data scientists will only grow as organizations increasingly rely on data-driven insights. We're now well into that period, and recruiters are finding it difficult to fill the growing need for talented data scientists. What motivates someone going into a data science career? For one thing, data science applies to almost any discipline. So, if you have the aptitude and desire to work with data, enjoy coding, have no problem learning math and statistics, and you are a good storyteller, then you can certainly enter a data science field and excel. For most people, this means acquiring additional tools and skills and continuously learning about new tools and techniques in the field. The Women in Data Science Initiative, spearheaded by the Stanford Institute for Computational and Mathematical Computing, have committed to inspire and educate data scientists worldwide, regardless of gender, and to support women in the field. When you are seeking a career in data science, you need to make sure your skill set matches the role you are targeting. You can tailor your skill set to the specific area you want to enter, adding missing skills via one of the many excellent online training resources. Then you'll be prepared for a fascinating and rewarding career. So now it is time to move into this field when there are such diverse choices available and education resources that make it a reality.
Learn how to program, learn some math, take a course in probability, learn a little bit of statistics, and then play. Build something. Write something. I mean, when I say build, programming and building systems, building things isn't just physical, right? You can build computer systems, statistical systems, whatever. But once you try to do something, and then you'll know what tools you need, right? And you'll say, oh my God, there's this expression there. What does an inner product mean? What's that? Okay, I can learn that. And then when they get to college, they will have a big jump on many of the other college students. And so when they get out of college, they'll have an even bigger jump and they'll make a lot of money. And they'll be happy too. This stuff is fun, right? It's fun.
If you're in high school and you're considering data science, I would say get familiar with databases. Start learning SQL. Start thinking about, computer science if that's interesting. If you have a computer science course in your school, take it. And that's a good part of being a data scientist. Beyond that, there are probably just ways to foster your creativity, right? Your curiosity. If you like detective games, that's kind of cool, right? If you like, treasure hunts or whatever, right? If you're into that stuff, I think you'll and you get an opportunity to do that stuff, that will help you as a data scientist because it's a really a good way to kind of make sure that you can be curious as you go about, your daily life. Encourage the curiosity, encourage the experimentation. It's kind of like science fairs, right? Science fairs are great, and they encourage that experimentation, that learning from, asking a question and answering it through a scientific method, but doing that with, data sets rather than vinegar volcanoes, right? It's kind of the same thing, but learning from data. And if we're going through an election season right now, there's a lot of stuff in the news about polls and survey results, and that's a great way to start a conversation to talk about how did the people who ran the polls, how did they know, how can they predict what's going to happen in the election? And so that's another kind of cool way to start a conversation about data science. Say encourage the person who is interested in data science because to pursue it, because it's a great career and it's something that's definitely going to be in need in the future. It's one of those highly sought after kind of knowledge professions that are really important to businesses around the world, so being a data scientist and being able to help companies as they grow and learn how to do things more efficiently or how to do things smarter, there'll always be a need for people like that, and data scientists are those people. I would say that I understand what you're talking about because I was never a great mathematics student as well. And I think there's actually a bunch of data scientists who are really successful and popular who are in the same boat. You know, there's kind of arithmetic and math in school is not necessarily everybody's best subject. But when you combine it with, you know, these aren't just, you know, hypothetical numbers. These aren't just, you know, problem statements that you have no connection to. When you have a connection to the problem, it suddenly becomes much easier to use math to help understand it, I've found. And so, you know, knowing the people who will benefit from the math that you do, I think is really cool.